For most of human history, the night sky seemed timeless. The stars appeared, fixed, the constellations never changed, and the universe felt calm, distant, and eternal. Yet hidden within that peaceful darkness lies a remarkable truth. When we look into space, we are not simply looking across vast distances. We are looking back through time itself. The light arriving in our eyes tonight did not begin its journey yesterday. Some of it left its source hundreds of years ago. Some began traveling long before the first civilizations were built, and some has been crossing the cosmos for billions of years. Every telescope ever constructed has been, in a sense, a time machine. The farther we look, the further back we travel, past galaxies, past stars, past entire chapters of cosmic history, until eventually we arrive at a time when the universe itself was still young. A time before planets, before the Milky Way had fully taken shape, before our sun existed, before Earth was even imaginable. For decades, astronomers believed they understood how this ancient universe evolved. The story seemed straightforward. After the Big Bang, the universe slowly cooled. The first stars ignited. The first galaxies emerged. And over billions of years, those galaxies gradually grew into the vast cosmic structures we see today. It was not a perfect story, but it was a story supported by decades of observations. A story refined by generations of scientists. A story that appeared to fit the evidence remarkably well. Then, humanity built a new eye, an instrument designed to peer deeper into time than any telescope before it. A machine capable of capturing ancient light that had been traveling across the universe for nearly its entire existence. Its mission seemed simple. Look farther, see earlier, reveal the universe's forgotten beginnings. And at first, that is exactly what it did. But as the first observations arrived, something unexpected began to emerge. The earliest galaxies did not look the way they were supposed to. They appeared brighter, larger, more developed, more mature, as if they had somehow skipped entire stages of cosmic growth. It was as though an archaeologist had uncovered a thriving city in a layer of rock where only primitive villages should exist. The deeper astronomers looked, the stranger the picture became. Again and again, ancient galaxies appeared where none were expected. Again and again, those galaxies seemed too advanced for their age, too bright, too massive, too active. Too soon at first, many assumed there must be a mistake. Perhaps the distances were wrong. Perhaps the measurements were misleading. Perhaps the ancient light had been misunderstood. After all, extraordinary claims demand extraordinary evidence. Yet with each new observation, the mystery only grew. The evidence refused to disappear. Instead, it multiplied, and slowly, a quiet question began spreading through the scientific community. What if the earliest chapters of cosmic history were not as simple as we believed? What if the young universe was not a slow and gentle place? What if it grew up faster than anyone imagined? Tonight, we begin a journey toward that question, a journey across billions of years, across oceans of darkness, across the faint glow of the first stars. We will travel back toward the dawn of galaxies, toward an era when the universe was still finding its shape, and along the way, we will encounter discoveries that challenge some of our most trusted assumptions. Not because they prove everything we know is wrong, but because they remind us how much remains unknown. The universe has always been willing to reveal its secrets, yet it rarely does so all at once. Instead, it offers clues, fragments, whispers carried by ancient light. And perhaps nowhere are those whispers more intriguing than at the very edge of cosmic history. To understand why these distant galaxies seem so impossible, we must first understand how humanity learned to read messages sent from more than 13 billion years in the past. Imagine standing beneath a perfectly clear night sky. Far above you, thousands of stars shine against the darkness. To our eyes, they seem immediate, present, as though their light belongs to this very moment. Yet that feeling is an illusion. Every point of light in the night sky is a message from the past. Even the moon, our closest celestial companion, is not seen exactly as it is now. Its light requires a little more than 1 second to reach Earth. When you look at the moon, you are seeing it as it was just over a second ago. The sun is farther away. Its light takes about 8 minutes to arrive. If the sun were to suddenly disappear, we would continue seeing it shining in the sky for 8 more minutes before darkness arrived. As distances grow larger, the delay grows larger as well. The nearest star beyond our sun sends us light that began its journey more than 4 years ago. Many of the bright stars visible at night are seen as they existed decades, centuries, or even thousands of years in the past. And when we turn our telescopes toward distant galaxies, the scale becomes almost impossible to comprehend. Some galaxies are so far away that their light began traveling toward us long before humans built cities. Others sent their light before agriculture existed. Some started their journey before our species had even appeared on Earth. The universe does not allow us to see distant objects as they are today. Instead, distance and time become intertwined. The farther away something is, the further back in history we see it. Astronomers sometimes describe this as looking through a cosmic archive. Every layer of distance reveals an older chapter of the universe. Nearby galaxies show us the recent past. More distant galaxies reveal earlier ages. And the most distant light of all carries us toward the very beginning. This remarkable relationship between distance and time is what makes astronomy unlike any other science. A geologist studies ancient rocks. A paleontologist studies ancient fossils. But astronomers can observe the past directly, not through remains, not through traces, but through the actual light that left distant objects billions of years ago. Every photon arriving at a telescope is a tiny messenger, a traveler that has crossed unimaginable distances, a witness to events that occurred long before Earth became what it is today. For generations, scientists dreamed of pushing this cosmic time machine farther than ever before. They wanted to answer some of the oldest questions humanity has ever asked. What were the first stars like? When did the first galaxies appear? How did darkness give way to light? And what did the universe look like during its earliest ages? Answering those questions required looking deeper into space than ever before. Yet that challenge came with a problem. The oldest light in the universe does not reach us unchanged. As the universe expands, space itself stretches, and as space stretches, light stretches with it. Imagine drawing waves on a rubber band. As the band is pulled apart, the waves become longer. Light behaves in much the same way. The ancient light traveling across billions of years becomes stretched by the expansion of the cosmos. Its wavelengths grow longer, its colors shift. What once began as visible light slowly drifts into infrared light, and the older the light is, the more dramatic that shift becomes. This means that the earliest galaxies are not merely distant, they are hidden. Their ancient glow has been stretched beyond what ordinary telescopes can easily detect, like whispers fading into the darkness, like the final echoes of a story nearly lost to time. For decades, this hidden frontier remained just beyond our reach. Scientists knew the earliest chapters of cosmic history were out there. They knew the answers were traveling toward us on ancient beams of light. But they lacked the instrument capable of capturing them. The first pages of the universe remained sealed, waiting, silent, patient, and to open those pages, humanity would need to build the most powerful space observatory ever created. A telescope unlike anything that had come before. A telescope designed specifically to see the oldest light in existence. And that telescope would become known as James Webb. For much of the 20th century, astronomers could only dream of seeing the universe's earliest moments. The problem was never a lack of curiosity. It was a lack of vision. The oldest galaxies were simply too far away. Their light too faint, their signals too stretched by cosmic expansion. Humanity needed a new kind of telescope, one designed not merely to look far into space, but to look far into time. For years, the most famous eye in space was the Hubble Space Telescope. Launched in 1990, Hubble transformed our understanding of the cosmos. Its images revealed breathtaking nebulae, distant galaxies, exploding stars, and entire regions of space that had never been seen before. Yet even Hubble had limits. As powerful as it was, it could only peer so deeply into the ancient universe. Beyond a certain point, the oldest light became too red, too stretched, too faint. It slipped beyond Hubble's reach, like trying to hear a whisper from across an ocean. Astronomers knew that somewhere beyond that limit lay an unexplored era, a time known as cosmic dawn, the age when the first stars ignited, when the first galaxies emerged from darkness, when the universe began transforming into the place we know today. But reaching that era would require a telescope built for a different purpose. A telescope designed to see infrared light, because infrared light holds a special advantage. It allows us to detect ancient signals that have been stretched by billions of years of cosmic expansion. Light that began as visible radiation in the young universe arrives today as infrared, invisible to human eyes, but not invisible to the right instruments, and so began one of the most ambitious engineering projects in human history. For decades, scientists and engineers worked toward a single goal: building a machine capable of capturing the oldest light ever observed. The result was unlike anything humanity had ever placed in space. At its heart sat a giant mirror, more than 6 meters across, made from 18 hexagonal segments, each coated with a thin layer of gold. Not because gold is beautiful, though it certainly is, but because gold reflects infrared light exceptionally well. Together, these mirrors would act as one enormous eye, gathering faint ancient photons that had traveled across the cosmos for more than 13 billion years. Yet the mirror alone was not enough. Infrared observations require extreme cold. Even a small amount of heat can interfere with the delicate signals arriving from deep space. The telescope needed protection, a shield unlike any ever constructed. A vast sun shield roughly the size of a tennis court. 5 ultra-thin layers working together to block heat from the sun, earth, and moon, keeping the telescope cold enough to detect the faintest whispers of the early universe. Once launched, the telescope traveled far beyond Earth's orbit, not toward another planet, not toward a distant moon, but toward a special location known as Lagrange Point 2, or simply L2, located nearly 1.5 million kilometers from Earth. L2 allows a spacecraft to maintain a stable position relative to both Earth and the Sun from there. James Webb could keep its giant shield permanently facing sunlight, while its sensitive instruments remained hidden in darkness, cold, quiet, watching, waiting, listening. It is a fitting image. A golden observatory floating in the darkness beyond Earth, patiently collecting ancient messages that began their journeys before our planet even existed. And when James Webb finally opened its eye to the universe, expectations were enormous. Scientists hoped to glimpse the first galaxies, to study the birth of stars, to refine existing models of cosmic evolution, perhaps even solve a few lingering mysteries. What few expected was that the telescope would almost immediately uncover new mysteries of its own. Because when James Webb looked toward the earliest galaxies ever observed, it did not simply confirm the old story. Instead, it revealed something deeply unsettling. The first galaxies appeared far more developed than anyone had predicted. As if the universe had been in a hurry, as if entire chapters of growth had unfolded much faster than our theories allowed. And those unexpected galaxies would soon become the center of one of the most fascinating scientific puzzles of the modern era. To understand why, we must now travel to the edge of observable history, to the moment when humanity first began seeing the earliest galaxies ever discovered. Long before Earth existed, long before the sun began shining, long before the Milky Way became the vast spiral galaxy we know today, the universe was a very different place. It was smaller, hotter, darker, and far less organized. The familiar cosmic landscape we see today had not yet emerged. There were no mature galaxies stretching across hundreds of thousands of light years. No generations of stars enriching space with heavy elements. No planets orbiting stable suns. The universe was still in its infancy. And yet, somewhere within that darkness, the first galaxies began to appear. For decades, astronomers could only imagine what those primordial galaxies might have looked like. Computer simulations painted a picture of gradual growth. Small clouds of matter gathered together. Gravity slowly pulled gas into denser regions. The first stars ignited. Tiny galaxies formed. Then, over hundreds of millions and billions of years, those galaxies merged and expanded into larger structures. The process resembled the growth of a city, beginning with scattered settlements, slowly expanding into towns, then cities, then sprawling civilizations. The earliest galaxies, according to this picture, should have been relatively small, relatively faint, and relatively simple. They were expected to represent the universe's first cautious steps, not giant leaps. When James Webb began looking toward cosmic dawn, scientists hoped to finally observe these ancient pioneers. And in many ways, the telescope succeeded beyond expectations. Almost immediately, Webb started detecting galaxies farther away than any previously observed. Each discovery pushed deeper into cosmic history. Each observation carried astronomers closer to the moment when the first galaxies emerged from darkness. It was exactly what the telescope had been built to do. At first, excitement spread through the scientific community. The images were extraordinary, tiny smudges of light, barely visible, yet each one represented an entire galaxy, a vast collection of stars existing billions of years ago. The farther away a galaxy appeared, the younger the universe had been when its light began traveling toward us. Some of these galaxies were seen as they existed less than 1 billion years after the Big Bang. Others appeared even earlier, 600 million years, 500 million years, 400 million years. Each new observation pushed closer toward the beginning, closer toward the first chapters of cosmic history. And that is when something unexpected started to happen. The galaxies did not seem to match the predictions. They were there, exactly where astronomers hoped to find them. But they did not look the way they were supposed to look at first. The differences seemed subtle. A galaxy appeared slightly brighter than expected. Another seemed larger. A third contained more stars than theoretical models predicted. Individually, none of these observations appeared alarming. Science often encounters small surprises. Most eventually find ordinary explanations. Yet as more data arrived, the pattern became harder to ignore. Again and again, ancient galaxies appeared unusually bright. Again and again, they seemed surprisingly mature. Again and again, they looked older than they should. Imagine opening a history book and discovering photographs of modern skyscrapers in a chapter about ancient villages. At first, you would assume there must be some mistake. A printing error, a misunderstanding, something placed in the wrong section. Yet what if every page showed the same anomaly? At what point would you begin questioning the story itself? That was the situation astronomers found themselves facing. The deeper Webb looked into the early universe, the more difficult it became to reconcile observation with expectation. The universe appeared to be growing up far too quickly. Galaxies seemed to be forming stars at astonishing rates, building structure at extraordinary speed, maturing long before existing theories believed possible. Still, scientists remained cautious. Extraordinary discoveries require extraordinary scrutiny. These galaxies existed at unimaginable distances. Their light was faint, their signals difficult to interpret. Perhaps the observations were misleading. Perhaps the galaxies were not as distant as they appeared. Perhaps the measurements contained hidden errors. After all, history is filled with scientific mysteries that eventually vanished under closer examination. Many researchers suspected this puzzle would follow the same path. As more precise measurements arrived, the apparent contradictions would likely disappear. The universe would return to behaving exactly as expected. The old models would survive. The mystery would fade. It seemed like a reasonable assumption. In fact, it was probably the most comfortable explanation available. But science is not concerned with comfort. Science follows evidence. And as astronomers began testing these surprising galaxies more carefully, the evidence delivered an answer few were prepared to hear. The galaxies were not disappearing. If anything, they appeared even more remarkable than they first seemed. And soon, researchers would perform a test capable of determining whether these ancient objects truly existed where Webb claimed they did. A test that would either rescue the old picture of cosmic history or deepen the mystery dramatically. For a brief moment, many astronomers believed the mystery might resolve itself. The history of science is filled with apparent contradictions that eventually disappear. A strange signal turns out to be instrumental noise. An unusual observation is traced back to a measurement error. A surprising result vanishes when better data arrives. It happens often, which is why scientists rarely rush toward extraordinary conclusions. The early galaxies discovered by James Webb seemed likely to follow the same pattern. They were incredibly distant, extremely faint, and difficult to study. Surely there was room for misunderstanding. Surely the universe had not rewritten its own history overnight. Yet as more observations arrived, the puzzle refused to go away. Instead, it became harder to ignore. The first hint came from the sheer number of unusual galaxies. If only one or two objects appeared brighter than expected, they could easily be dismissed as exceptions. But Webb was finding many of them, again and again, across different regions of the sky, across different observing programs. Across different teams of astronomers, the same strange pattern kept appearing. Galaxies that looked too large, too bright, too evolved for a universe that was supposedly still in its infancy. Imagine arriving at an archaeological site believed to be only a few decades old. Instead of simple shelters and primitive tools, you discover paved roads, libraries, monuments. evidence of generations of development. The findings would not merely raise questions about the site, they would raise questions about the timeline itself. Something similar was beginning to happen in astronomy, because according to standard cosmological models, building large galaxies requires time. A lot of time. Stars must form, live their lives, create heavier elements, explode, enrich surrounding gas. Then, new generations of stars form from that enriched material. Galaxies grow through mergers. Matter accumulates. Structure becomes increasingly complex. None of this is expected to happen overnight. Cosmic evolution is usually portrayed as a gradual process, patient, step by step. Yet Webb seemed to be observing galaxies that had already raced far ahead in that process. Some appeared to contain enormous numbers of stars. Others seemed surprisingly massive. Several looked comparable to galaxies that should not have existed until much later in cosmic history. The implications were difficult to ignore. If the observations were correct, something was allowing galaxies to grow far more rapidly than expected. Perhaps the first stars formed faster. Perhaps gravity assembled matter more efficiently. Perhaps some ingredient was missing from existing models. Or perhaps the measurements themselves were misleading. Among those possibilities, the last option remained the most attractive. Not because scientists wanted it to be true, but because it required the fewest changes to our understanding of the universe. The challenge was determining whether the distances were accurate. When astronomers observe extremely distant galaxies, they often estimate distance using a technique called photometric redshift. Without diving too deeply into technical details, the method works by measuring how a galaxy's light appears across different wavelengths. Certain patterns allow researchers to estimate how far that light has traveled. It is a powerful technique, and it has enabled countless discoveries. Yet it is still an estimate, a very sophisticated estimate, but an estimate nonetheless, and estimates can sometimes be wrong, especially when studying objects near the limits of observation. This possibility offered a comforting explanation. Maybe these galaxies were not truly ancient. Maybe they were closer than they appeared. Perhaps dust, unusual light sources, or other effects were creating illusions. If that were the case, the mystery would disappear. The galaxies would no longer be impossible. The timeline would remain intact. The standard picture of cosmic history would survive largely unchanged. For a while, many researchers hoped this would be the outcome, because the alternative was far more unsettling. The alternative suggested that the universe itself was behaving differently than expected. And if that were true, astronomers would need much stronger evidence before accepting such a conclusion. Fortunately, there was a way to obtain that evidence, a far more precise method. A method capable of measuring cosmic distances with much greater confidence. Unlike photometric estimates, this technique could directly reveal how much the light from a galaxy had been stretched during its journey across the universe. It was slower, more difficult, and required valuable observing time, but it offered something priceless: certainty. Astronomers knew that sooner or later, the most surprising galaxies would have to face this test, and when they did, one of two things would happen. Either the mystery would finally disappear, or the evidence would confirm that these galaxies truly existed at the dawn of cosmic history. If the second outcome proved true, the implications would be profound, because it would mean the universe had assembled entire galaxies far earlier than anyone thought possible, and that possibility was about to be tested. The results would soon arrive, and for many astronomers, they would be far more troubling than anyone expected. Whenever science encounters something unexpected, the first question is rarely, have we discovered something new? More often, the first question is much simpler. Have we made a mistake? It is a habit built over centuries. And for good reason, the universe has a remarkable ability to surprise us. But observations can also be deceiving, in astronomy especially. Appearances are not always what they seem after all. Astronomers cannot travel to distant galaxies. They cannot collect samples. They cannot visit these ancient worlds directly. Everything they know comes from light. Tiny streams of photons crossing unimaginable distances before reaching a telescope. From that faint light, scientists must reconstruct entire histories, estimate distances, measure masses, determine ages, and sometimes those measurements prove difficult. The earliest galaxies discovered by James Webb were among the most challenging objects ever observed. Now, not because they were large, not because they were bright, but because they were unimaginably far away. The farther an object lies from Earth, the more its light becomes stretched by the expansion of the universe. This stretching shifts light toward longer wavelengths, a phenomenon known as redshift. Redshift is one of the most important tools in modern astronomy. It acts almost like a cosmic ruler. Though, the greater the redshift, the farther away an object generally is, and the farther away it is, the further back in time we are seeing. For the most distant galaxies, measuring redshift becomes absolutely critical. Small error can dramatically alter our understanding of where an object sits in cosmic history. And this is where the debate began. Many of Webb's earliest discoveries relied initially on photometric redshift estimates. These estimates are created by analyzing how bright an object appears through different filters. The method is powerful, efficient, and often remarkably accurate. Yet it has limitations, particularly when studying extremely distant objects that push observational technology to its limits. Some astronomers wondered whether the strange galaxies were simply being misidentified. Perhaps they were not ancient galaxies at all. Perhaps they were closer galaxies disguised by dust. Perhaps unusual stellar populations were confusing the calculations. Perhaps something else entirely was producing the illusion. It would not be the first time nature had played such tricks. The history of astronomy contains many examples of mistaken identities. Signals once believed to be revolutionary discoveries later found perfectly ordinary explanations. Scientists understood this, which is why skepticism spread quickly. Research papers appeared, conferences filled with debate. Teams examined the data from every possible angle. The discussion was not driven by disbelief, it was driven by caution. Extraordinary claims require extraordinary evidence. And the idea that mature galaxies existed only a few 100 million years after the Big Bang was certainly extraordinary. If the measurements were wrong, the mystery would disappear. The universe would remain comfortably familiar. The timeline would survive. Theoretical models would require only minor adjustments. Many researchers quietly hoped this would be the outcome. Not because they feared new discoveries, but because science progresses most smoothly when observations and theory move together. Yet the more carefully astronomers examined the evidence, the more uncomfortable the situation became. The galaxies continued appearing in different surveys, different observing campaigns, different regions of the sky. Independent teams kept reaching similar conclusions. Again and again the same pattern emerged. The objects looked ancient, very ancient, too ancient. The possibility of widespread error became increasingly difficult to maintain. Still, estimates were estimates. No matter how sophisticated the analysis, the galaxies had not yet faced the most rigorous test available. And that distinction mattered, because there exists another method, a method far more precise than photometric measurements, a technique capable of reading hidden information directly from the light itself. If photometric redshift is like estimating someone's age from a photograph, this second technique is more like reading their birth certificate. Instead of measuring broad patterns of brightness, it breaks light into its individual components, every wavelength, every fingerprint, every clue embedded within the signal. This process is known as spectroscopy, and for decades, spectroscopy has served as one of astronomy's most trusted tools. Because light carries information, far more information than our eyes can perceive. Within a beam of starlight are signatures of motion, distance, temperature, chemistry, and history, like a coded message waiting to be decoded. If these mysterious galaxies were truly ancient, spectroscopy would reveal it. If they were imposters, spectroscopy would expose them. There would be little room left for ambiguity. Soon, James Webb turned its instruments toward the most surprising candidates. Astronomers waited. The stakes were enormous. One outcome would restore confidence in existing models. The other would deepen the mystery dramatically. For a time, nobody knew which answer the universe would provide. But when the results finally arrived, they delivered a message that was impossible to ignore. The galaxies were not where scientists hoped they would be. They were exactly where the observations said they were. And suddenly the mystery became much harder to explain. For a while, uncertainty provided a kind of comfort. As long as the distances remained estimates, there was still room for doubt, room for alternative explanations, room for the possibility that the universe was behaving exactly as expected. But science eventually demands stronger answers. And in this case, those answers would come from spectroscopy. Unlike ordinary images, which show only brightness and shape, spectroscopy reveals the hidden structure of light itself. Imagine hearing a distant orchestra through a wall. You might recognize the music. You might estimate how many instruments are playing. but much of the detail would remain hidden. Now imagine removing the wall entirely. Suddenly every note becomes clear. Every instrument can be identified. Every subtle variation can be heard. That is what spectroscopy does for astronomers. It transforms faint light into information. And when James Webb applied this technique to the most surprising early galaxies, the results were extraordinary. Each galaxy carried a unique fingerprint, the record of how much its light had been stretched during its journey across the expanding universe. The measurements were precise, direct, difficult to dispute, and one by one, the galaxies revealed their true distances. Some existed when the universe was less than 1 billion years old. Others appeared even earlier, far earlier. A few belonged to an era when the cosmos was only a few 100 million years old, an age so remote that it sits close to the very beginning of galactic history. The implications were immediate. These galaxies were not nearby imposters. They were not ordinary objects masquerading as ancient ones. They were genuinely distant, genuinely old, or more accurately, they were being observed at a time when the universe itself was astonishingly young. The mystery that many hoped would disappear had survived its most difficult test, and in some ways, it had become even more troubling. Because now astronomers had to confront a new reality. The galaxies were real, the distances were real, which meant their properties were real as well. Their brightness, their apparent mass, their surprising level of development. All of it now demanded explanation. For decades, computer simulations had attempted to recreate the growth of the universe. These simulations began shortly after the Big Bang. Matter gradually gathered under gravity. Small structures formed. Larger structures emerged. Galaxies slowly assembled over immense stretches of time. The process was elegant, and for many observations, remarkably successful. Yet the galaxies James Webb was finding seemed unwilling to follow that script. They looked as though they had skipped entire stages of development, but like trees appearing before their seeds, like cities appearing before their foundations. The timeline itself seemed compressed. Events that should have taken much longer appeared to be happening with astonishing speed. Some researchers described the situation as a tension. Others called it a discrepancy. A few began using a stronger word, crisis, not because the existing model had failed completely. Far from it. The standard cosmological model still explained countless observations with remarkable accuracy, but these new galaxies had exposed a crack. A small crack, perhaps, yet one that could not simply be ignored. And as more observations arrived, that crack seemed to widen. The universe was not merely producing galaxies earlier than expected. It was producing galaxies that appeared unusually energetic, unusually active, almost as if the young cosmos had been working overtime. Imagine visiting a forest that should contain only saplings. Instead, you find towering trees already reaching toward the sky. You could question your measurements, you could question your assumptions, but eventually you must confront another possibility. Perhaps the forest simply grew faster than expected. That possibility was becoming increasingly difficult to avoid. The early universe appeared far more productive than anyone had imagined. Stars were forming, galaxies were assembling, quantum structure was emerging, and all of it seemed to be happening at remarkable speed. Yet among all the surprising properties these galaxies possessed, one stood above the rest: their brightness. Because brightness tells a story about stars, energy, growth, and activity. The brighter a galaxy appears, the more power it is producing. And some of these ancient galaxies were producing far more power than they should have been capable of generating. The deeper astronomers looked into the young universe, the more they encountered the same unsettling pattern: bright galaxies, again and again, far brighter than theory predicted. And that raised a new question. Perhaps the most important question so far. If these galaxies truly existed at the dawn of cosmic history, what was making them shine so intensely? Once astronomers accepted that these galaxies were truly ancient, their attention shifted to another mystery. A mystery hidden within the light itself. Because distance was only part of the problem, brightness was the other. And in some ways it was even harder to explain. At first glance, brightness might seem like a simple thing. A galaxy shines. A telescope detects that light. The brighter the object appears, the more light it produces. Simple. Yet, behind that simplicity lies a profound question. Where does that light come from? For most galaxies, the answer is straightforward. Stars. Lots of stars. Every star is a giant nuclear furnace. Deep within its core, hydrogen atoms fuse together, releasing enormous amounts of energy. That energy eventually escapes into space as light. A galaxy containing billions of stars becomes a vast ocean of starlight. The more stars it contains, the brighter it appears. But this is where the mystery begins. Many of the galaxies discovered by James Webb appeared far brighter than expected for their age. Not slightly brighter, significantly brighter, bright enough to challenge existing models of cosmic evolution. To understand why this matters, imagine building a city. A larger city requires more buildings, more roads, more people, more resources. All of those things require time. The same logic applies to galaxies. A brighter galaxy generally requires more stars. More stars require more gas. More gas requires more structure, and all of that requires time. Time that the early universe seemingly did not have. Yet, there they were. Ancient galaxies shining with astonishing intensity. Some appeared capable of producing light equivalent to billions of suns, at an age when the universe was only a tiny fraction of its current age. It was as though someone had skipped years of construction and somehow arrived at the finished result. Naturally, astronomers began searching for explanations. Perhaps the galaxies were forming stars at extraordinary rates, far faster than anything commonly seen today. After all, the young universe was different. Gas was more abundant. Conditions were more extreme. Maybe the first galaxies were simply much more efficient at turning gas into stars. This possibility seemed reasonable, at least at first. But as researchers examined the numbers more carefully, the situation became uncomfortable. To generate that much light, some galaxies would need to produce stars at extraordinary speeds, almost continuously, without pause, without interruption, like cosmic factories operating around the clock. Even then, the calculations often struggled to match the observations. The galaxies still seemed too bright, the numbers still seemed too large, the universe still seemed to be moving too quickly, and brightness creates another problem. Because stars are not eternal, the brightest stars live fast and die young. They burn through their fuel rapidly. Some survive only a few million years before ending their lives in powerful explosions. This means that maintaining extreme brightness requires a constant supply of new stars, generation after generation, a relentless cycle of birth and death. The early galaxies appeared to be sustaining exactly that kind of activity, which suggested something remarkable. The young universe may have been far more energetic than astronomers once believed, far more productive, far more intense. Imagine standing on a hill overlooking a city at night. The brighter the city appears, the more activity is taking place below. Lights in homes, traffic on roads, factories operating, people moving, energy flowing. Brightness becomes evidence of activity. The same principle applies to galaxies. When astronomers looked at these ancient systems, they were not merely seeing light, they were witnessing activity, growth, transformation, evidence that vast amounts of matter were being converted into stars at astonishing speed. And yet, the brightness itself was only part of the story, because light carries more than intensity, carries information. Hidden within that ancient glow were clues about the materials from which these galaxies were made, clues about their history, their stars, their past. And when astronomers began studying those clues, they encountered something even more surprising. The galaxies did not merely appear too bright, they appeared too mature, because buried within their light were chemical fingerprints that should not have existed so early in cosmic history. Elements that required generations of stars to create, elements that should have needed much more time. And somehow, those elements were already there, waiting within the light, waiting to tell a story that was even stranger than the brightness problem itself. To understand that story, we must look beyond the light these galaxies produced, and begin examining what that light was made of. When most people look at the night sky, they see stars, points of light scattered across the darkness, beautiful, distant, mysterious. But astronomers see something else. They see chemistry, because every star is more than a source of light. It is also a factory that slowly manufactures the ingredients of the universe. In the beginning, the cosmos was surprisingly simple. Shortly after the Big Bang, most of the universe consisted of only a few basic elements. Hydrogen dominated, helium followed. Tiny traces of lithium existed as well, and that was largely it. The universe contained no oxygen, no carbon, no iron, no calcium, no gold. None of the heavier elements that would eventually become planets, oceans, mountains, or living creatures. Those ingredients did not yet exist. The early universe was chemically primitive, a vast ocean of hydrogen and helium stretching across space. The heavier elements had to be created later, and the only places capable of creating them were stars. Deep inside stellar cores, nuclear fusion slowly transforms lighter elements into heavier ones. Hydrogen becomes helium. Helium helps create carbon. Carbon contributes to the formation of oxygen and other elements. As stars evolve, increasingly complex chemistry unfolds within their interiors then. When massive stars die, they scatter those newly created elements back into space. The next generation of stars forms from that enriched material. Over time, the universe becomes chemically richer, more complex, more diverse. In many ways, the history of the cosmos can be told as a history of chemical evolution. And that evolution follows a timeline, a chemical clock. The earliest stars should contain almost no heavy elements. Later generations should contain more. The longer a galaxy exists, the richer its chemical composition becomes. This principle has guided astronomical research for decades. It provides a way to estimate how much stellar activity has occurred within a galaxy. How many generations of stars have lived and died? How much time has passed? Which is why the observations from James Webb were so surprising. When astronomers analyzed the light from some of the earliest galaxies ever observed, they expected chemical simplicity. They expected systems still dominated by the universe's original ingredients. Instead, they found signs of enrichment, signs that heavier elements were already present. Carbon, oxygen, and other materials that should have required generations of stellar evolution. The discovery was not merely unexpected, it was deeply puzzling. Because heavy elements cannot appear by magic, they must be forged, created inside stars, then dispersed into space. That process takes time. Or at least, it was supposed to. Yet the galaxies Webb observed seem to have undergone significant chemical development astonishingly early. Imagine walking into a newly built town and discovering ancient libraries, weathered monuments, layers of history that should require centuries to accumulate. You would immediately wonder how those things appeared so quickly. Astronomers faced a similar dilemma. Chemical fingerprints suggested that these galaxies had already experienced multiple cycles of stellar birth and death, as if cosmic history had somehow accelerated, as if the universe had compressed entire chapters of evolution into a much shorter period. The implications were profound. If these measurements were correct, then the first stars may have behaved very differently than previously imagined. Perhaps they formed more rapidly. Perhaps they were much larger. Perhaps they lived brief but extraordinarily intense lives. A single generation of unusual stars might be capable of enriching galaxies far faster than conventional models predicted. This idea led researchers toward one of the most fascinating possibilities in modern astronomy: the existence of the universe's first stars. Not the stars we see today. Not stars like the Sun, but an ancient population unlike anything currently known. Stars born from a chemically pristine universe. Stars formed before carbon, before oxygen, before the familiar ingredients of later cosmic history. For decades, astronomers have referred to these hypothetical pioneers as population stars. No one has ever directly observed one, yet their existence is considered one of the most important missing chapters in the story of cosmic dawn. Because if population ID stars were real, they may have transformed the young universe at extraordinary speed. Some theoretical models suggest they could have been enormous, hundreds of times more massive than the Sun, brilliant beyond imagination, burning through their fuel at astonishing rates, living only brief lives before exploding with tremendous force. If such stars existed, they could help explain the chemical mystery. They could rapidly enrich, surrounding galaxies with heavier elements. They could accelerate cosmic evolution. They could provide part of the answer. But they would also create new questions, cause stars that massive would reshape the early universe in ways that extend far beyond chemistry. Their light would influence entire regions of space. Their radiation would help transform the cosmos itself. And if enough of them existed, they may have played a crucial role in ending one of the strangest eras in cosmic history, an era known as the Cosmic Dark Ages, a time when the universe was filled with darkness, time before the cosmos became transparent, a time before starlight could travel freely across space. To understand what happened next, we must journey into that forgotten age and explore how the first light began to change the universe forever. Before galaxies filled the cosmos with light, before planets formed around distant suns, before the Milky Way stretched across the darkness, the universe entered a strange and silent chapter of its history, chapter unlike anything we see today. Astronomers call it the Cosmic Dark Ages. It is one of the most mysterious periods in the entire story of the cosmos, not because nothing existed, but because almost nothing shined. The Big Bang had already occurred. The universe had expanded and cooled. Atoms had formed. Matter filled space. Yet stars had not appeared. Galaxies had not assembled. The universe was vast, but it was dark. Imagine standing in an endless landscape before the first sunrise. The terrain exists, the mountains exist, the rivers exist, but none of them can be seen, because light has not yet arrived. That was the state of the cosmos, a universe waiting for its first dawn. For millions of years, gravity worked quietly. Invisible clouds of hydrogen and helium drifted through space. Tiny variations in density slowly grew. Regions containing slightly more matter attracted even more matter. Gradually, those regions became denser, hotter, more compressed, until eventually, something extraordinary happened. The first stars were born. No human has ever seen these stars. No telescope has directly observed them. Yet nearly every astronomer believes they existed, because without them, the universe we know today could never have emerged. These first stars were unlike modern stars. The sun contains traces of heavier elements inherited from countless generations of ancient stellar ancestors. But the first stars had no such inheritance. They formed from a universe that was still chemically pristine, a universe made almost entirely of hydrogen and helium. And that difference may have changed everything. Modern stars form under conditions influenced by heavier elements. Those elements help gas cool efficiently. They influence how stars grow, how they evolve, and how massive they become. The first stars lacked those ingredients. As a result, many simulations suggest they may have grown to extraordinary sizes, far larger than the sun, perhaps 100 times more massive, perhaps 200 times. Some models suggest even greater extremes. These would not have been ordinary stars. They would have been cosmic giants, brilliant beyond imagination. A single one could outshine millions of modern stars, their surfaces blazing at incredible temperatures, their radiation flooding surrounding space. If such stars existed, they would have transformed the young universe almost immediately. Yet their greatness came with a price. Massive stars live fast. The larger the star, the shorter its life. While the sun may survive for billions of years, these primordial giants may have lived only a few million. Brief flashes in cosmic history, burning furiously before dying in spectacular explosions. Their lives were short, but their influence may have been immense, because during those brief lives, they would have begun creating the universe's first heavy elements. Carbon, oxygen, silicon, the ingredients that later generations of stars would inherit. And when these giants died, they would have scattered those elements into surrounding space. Suddenly, regions that had once been chemically simple became richer, more complex, more capable of forming new generations of stars. In this way, the first stars may have acted like cosmic accelerators, speeding up the growth of galaxies, enriching their environments, helping explain why some of Webb's earliest galaxies already appear chemically mature. Yet chemistry was only part of their legacy. The light of these primordial giants may have changed the universe itself, because during the cosmic dark ages, the cosmos was filled with neutral hydrogen. Thin fog spread across intergalactic space. Unlike ordinary fog, this cosmic fog did not block visibility in the familiar sense. Instead, it absorbed certain wavelengths of light, preventing radiation from traveling freely across vast distances. The universe was not entirely opaque, but it was far from transparent. Light struggled to move through it. Then the first stars appeared. Then everything began to change. The intense ultraviolet radiation produced by these stellar giants started tearing electrons away from hydrogen atoms, a process known as ionization. Wherever enough radiation accumulated, the fog began to dissolve. Small islands of transparencies emerged within the darkness, tiny bubbles of clear space surrounding the first sources of light. At first, these bubbles were isolated, scattered, separated by enormous distances, but as more stars formed, the bubbles expanded. They grew larger, they merged, they connected, and slowly, the darkness that had dominated the cosmos began to retreat. The first dawn was not a single moment. It was a gradual awakening, a transformation unfolding across hundreds of millions of years. Transformation powered by stars unlike any that would come later. If these stellar giants truly existed, they may help explain why the early universe appears so active, why galaxies seem to mature so rapidly, why heavy elements appear so early, why brightness becomes so intense. Yet even these cosmic monsters cannot answer every question, because astronomers are beginning to realize that something even larger was happening, not just within galaxies, but across the universe itself. The ancient fog was disappearing. The cosmos was becoming transparent, and according to some of Webb's observations, that transformation may have occurred far earlier than expected, which raises another mystery, one that reaches beyond individual stars and galaxies, a mystery involving the moment the entire universe emerged from darkness and stepped into the light. If you could travel back to the earliest ages of the cosmos, you would not find a universe filled with clear, open space. You would find something stranger, a universe wrapped in a vast cosmic fog. Not a fog of water droplets, not clouds drifting through the darkness, but an immense sea of neutral hydrogen stretching between the first galaxies. Invisible, yet profoundly important. This fog shaped the destiny of the early universe, and for hundreds of millions of years, it controlled how light moved through space. To understand why, we must return once more to the aftermath of the Big Bang. As the young universe expanded, it gradually cooled. Eventually, temperatures fell low enough for electrons and protons to combine. Hydrogen atoms formed. For the first time, light could travel relatively freely. The universe became transparent. This event left behind a faint glow that still surrounds us today. A glow known as the cosmic microwave background. But that transparency did not last forever. As the universe continued evolving, vast quantities of neutral hydrogen accumulated throughout intergalactic space. And neutral hydrogen has a peculiar property. It absorbs certain forms of energetic radiation, especially ultraviolet light. The result was a cosmos filled with matter that could trap and scatter radiation. A cosmic haze spread across the universe, not dense enough to block everything, but significant enough to shape the journey of light. For a long period, the universe existed in this state, dark, quiet, waiting. Then the first stars appeared, and the fog began to change. The immense radiation produced by those primordial stars started breaking apart hydrogen atoms. Electrons were stripped away. Neutral hydrogen became ionized hydrogen. The fog slowly dissolved. Astronomers call this transformation the Epoch of Reionization. It is one of the most important transitions in cosmic history, because once enough hydrogen became ionized, the universe grew increasingly transparent. Light could travel farther. Galaxies became visible across greater distances. The cosmos opened itself to observation. In many ways, the universe we know today emerged from this transformation. Without reionization, the modern cosmic landscape would look very different. Yet despite its importance, many details remain uncertain. For decades, astronomers believed they had a reasonable estimate for when this process occurred. Timeline seemed relatively clear. The first stars ignited. Small ionized regions formed. Those regions gradually expanded. Over hundreds of millions of years, the cosmic fog retreated. Eventually, most of the universe became transparent. It was a slow and elegant process, or so it seemed. Then James Webb arrived, and once again, the early universe appeared more complicated than expected. Several observations suggested that galaxies in the young cosmos were producing enormous amounts of radiation. Enough radiation to influence their surroundings far more dramatically than theoretical models predicted. The implication was difficult to ignore. If galaxies were forming stars faster than expected, and if those stars were producing extraordinary amounts of ultraviolet radiation, then reionization itself may have begun earlier and progressed more rapidly than anyone had anticipated. The universe may have cleared its fog sooner than expected. This possibility carried profound consequences, because reionization acts almost like a historical clock. Its timing tells us how quickly the first stars and galaxies transformed their environment. A slower reionization suggests gradual growth. Faster reionization suggests intense activity. And many of Webb's discoveries seem to favor the second possibility. The young universe appeared energetic, restless, productive, almost impatient, as if the first cosmic structures were racing to illuminate the darkness. Researchers began comparing observations with simulations. Again and again, they encountered familiar tensions. The galaxies seemed brighter, more numerous, more active. The ancient fog appeared to be retreating faster than expected. And if that interpretation proved correct, then something extraordinary must have been powering the process. Perhaps the first stars were even more efficient than current models suggest. Perhaps early galaxies formed in greater numbers. Perhaps entirely new mechanisms contributed to the transformation. Each possibility opened new questions, because the universe was not becoming transparent everywhere at once. Instead, reionization unfolded unevenly, patch by patch, region by region. The first stars created small pockets of clarity within the darkness. Tiny islands of light surrounded by a sea of cosmic fog. Those islands expanded over time. Eventually they touched, merged, and transformed the universe on a grand scale. This image has become one of the most beautiful in modern cosmology. A dark universe gradually punctured by growing bubbles of light. Each bubble marking a region where the first stars and galaxies had begun reshaping reality itself. And understanding those bubbles may hold some of the most important clues about cosmic dawn. Because within them lies a record of how the earliest structures grew, how quickly they spread, and how the young universe evolved into the transparent cosmos we inhabit today. To follow that story, we must leave behind individual stars, leave behind individual galaxies, and begin exploring the enormous expanding bubbles that carried the universe out of darkness and into light. From our perspective today, the universe appears remarkably uniform. No matter where we look, the same laws of physics apply, the same atoms exist, the same cosmic structures emerge, the same starlight travels through space. It is easy to imagine that the universe became transparent all at once, as though someone flipped a switch. Darkness ended, light began, the fog vanished. But reality was far more intricate, and far more beautiful. The transition from darkness to light unfolded gradually, not everywhere at the same time, not in a single dramatic moment, but through countless local transformations spread across the cosmos. To picture this process, imagine standing above a frozen lake at night. The surface is covered by ice, dark, silent, unbroken. Then small cracks begin to appear, tiny openings scattered across the frozen landscape. As time passes, those openings expand, growing wider, growing larger. Eventually they meet, connect, merge, until the ice is no longer a continuous sheet. Something similar occurred during the Epoch of Reionization. The first stars and galaxies did not illuminate the entire universe immediately. Instead, each source of light carved out its own region of transcendency, a small bubble within the cosmic fog. Inside these bubbles, hydrogen atoms became ionized. Light traveled more freely. The surrounding darkness retreated. At first, these bubbles were tiny, barely noticeable against the immense scale of the universe. One galaxy here, another there, a handful of stars illuminating their local surroundings. Yet every new source of radiation expanded the process. Each bubble grew, each bubble pushed farther into the fog, and over time, the young universe became a patchwork of darkness and light, a mosaic of expanding cosmic islands. This stage of cosmic history is difficult to observe directly. The bubbles themselves vanished billions of years ago, yet their existence is written into the structure of the universe, like footprints preserved in ancient stone. Researchers can reconstruct aspects of this transformation by studying distant galaxies, by measuring radiation, by comparing observations with simulations, and increasingly by using the remarkable capabilities of James Webb. What Webb has revealed is a universe that may have been changing faster than expected. The earliest galaxies appear surprisingly capable, not merely passive collections of stars, but active engines of transformation. Many seem powerful enough to influence enormous regions of space, producing radiation capable of reshaping their cosmic neighborhoods. 5. This realization has changed how scientists think about cosmic dawn. The first galaxies were not simply inhabitants of the young universe. They were architects of it. They helped determine how quickly darkness retreated, how rapidly transparency spread, how the cosmos evolved from its primitive beginnings. And yet, the story becomes even more fascinating, because the bubbles themselves may have influenced future galaxy formation. As regions became ionized, conditions changed. Matter flowed differently. Gas behaved differently. New opportunities emerged for stars and galaxies to grow. The universe was not merely clearing its fog, it was reshaping its future. Every bubble became part of a larger network, a growing web of transformation stretching across cosmic space. Eventually, those bubbles expanded enough to overlap. When two bubbles met, they created larger transparent regions. When many bubbles merged, entire sections of the universe became clear. The process accelerated. Darkness retreated more rapidly. Transparency spread. Until one day on cosmic timescales, the fog had largely disappeared. The universe had awakened. Light could now travel immense distances. Galaxies became visible across vast stretches of space. The stage was set for everything that followed. The galaxies, the stars, the planets, the civilizations, even us. In a very real sense, every observer who has ever looked at the night sky owes their existence to this transformation. Because, without reionization, the cosmos would have remained a profoundly different place. Yet despite all we have learned, important questions remain unanswered. How many galaxies participated in this process? How quickly did the bubbles grow? What kinds of stars powered them? And perhaps most intriguingly, were there other objects contributing to the transformation? Objects we do not yet fully understand. That question has become increasingly important in recent years, because among Webb's many discoveries lies a strange population of objects unlike anything astronomers expected to find. Small, distant, unusually red, and surprisingly abundant. At first they appeared almost insignificant. Tiny points of light hidden within deep observations. But the more researchers studied them, the stranger they became. Today they are known by a deceptively simple name, the little red dots, and they may represent one of the greatest mysteries of the early universe. By the time James Webb began revealing the earliest galaxies, astronomers had already become accustomed to surprises. Galaxies that appeared too bright, too massive, too chemically mature, too early. One mystery seemed to follow another. Yet, among all the unexpected discoveries emerging from the telescope's observations, few were as puzzling as a collection of tiny objects that initially seemed almost insignificant. They were small, faint, easy to overlook, and yet they appeared again and again, scattered throughout the distant universe, hidden among the countless sources of ancient light. At first, they looked like ordinary points of light, nothing particularly remarkable, just another set of distant objects waiting to be catalogued and studied. But as astronomers examined them more closely, a strange pattern emerged. These objects were unusually red, not merely red in the way distant galaxies often appear, but intensely red, remarkably red, enough to stand out even among the ancient populations James Webb was designed to observe. Soon they acquired a nickname, a simple name that captured their appearance as the little red dots. At first, the nickname sounded almost playful, yet behind it lay a serious scientific mystery, because nobody was entirely sure what these objects actually were. That uncertainty was unusual. Astronomers are accustomed to classifying cosmic objects, stars, galaxies, nebulae, quasars, black holes. Most discoveries eventually fit somewhere within existing categories. The little red dots resisted easy classification. They seemed too compact to be ordinary galaxies, too numerous to be dismissed as rare anomalies, and too strange to fit comfortably into theoretical expectations. The deeper researchers looked, the more questions appeared. Some little red dots seemed incredibly bright for their size. Others appeared to contain astonishing amounts of energy. Many existed during an era of cosmic history, when such objects were not expected to be common. It was as though Webb had uncovered an entirely new population hiding within the early universe. Population that previous telescopes had simply been unable to see. Imagine walking through a familiar forest. For years, you believe you understand every tree, every plant, every animal. Then, one day, a new kind of organism appears everywhere. Not rare, not isolated, but surprisingly common. Suddenly, you realize the forest was more complex than you imagined. That is the feeling many astronomers experienced when studying the little red dots. The objects seemed to be telling a story, yet nobody could agree on exactly what that story was. Several explanations quickly emerged. One possibility suggested that these objects were compact galaxies undergoing intense bursts of star formation. Perhaps they represented an extreme stage of galactic growth, a brief but powerful phase during which stars formed at extraordinary rates. Such activity could help explain their brightness. It could also explain their unusual colors. Yet there were problems. Some observations suggested that star formation alone might not account for all the energy being produced. The numbers simply seemed too extreme. Another possibility soon gained attention. Perhaps the little red dots were not primarily powered by stars at all. Perhaps something else lay hidden at their centers. Something far more dramatic, a growing black hole. This idea immediately captured interest, because black holes surrounded by infalling matter can produce enormous amounts of radiation. Gas spiraling toward a black hole becomes compressed and heated. Temperatures rise. Energy is released. The surrounding region can shine brilliantly, sometimes outshining entire galaxies. If young black holes were hiding inside the little red dots, many of the observations would begin to make sense. Their compact appearance, their unusual brightness, their abundance during the early universe. Suddenly, the mystery became even larger, because black holes introduce a new challenge already lurking elsewhere in Webb's discoveries: growth. The universe was young, extremely young. If these objects truly contained massive black holes, those black holes must have grown with astonishing speed, perhaps faster than existing theories allowed. The same question that haunted the early galaxies now returned in a new form. How was everything growing so quickly? Galaxies, stars, chemical complexity, and now perhaps black holes as well. The little red dots seemed less like an isolated puzzle and more like another symptom of a larger mystery. Again and again, the early universe appeared unusually productive, unusually efficient, almost impatient, as if cosmic evolution had accelerated during its earliest chapters. Researchers continue studying these objects today. Some evidence supports intense star formation. Other evidence points toward active black holes. Perhaps both explanations are correct. Perhaps the truth is something entirely unexpected. The universe has a habit of choosing answers nobody initially considered. For now, the little red dots remain one of James Webb's most intriguing discoveries. Tiny points of ancient light, barely visible across billions of years, yet capable of challenging our understanding of cosmic history. And if black holes truly lie hidden within many of these mysterious objects, then another question immediately follows, a much larger question. Because some of the earliest black holes discovered by James Webb appear far too massive, far too developed, far too old for the age of the universe in which they exist. Once again, the cosmos seems to be confronting us with the same unsettling message: too much, too soon. And nowhere is that message more difficult to explain than in the story of the first supermassive black holes. There are few objects in the universe more mysterious than black holes. They cannot be seen directly. They emit no light of their own. No telescope can photograph them in the traditional sense. And yet their presence can reshape entire galaxies. For decades, astronomers believed they understood the broad outline of how black holes grow. A massive star dies, its core collapses. The black hole is born. Over millions and billions of years, that black hole gathers matter. Gas falls inward. Stars wander too close. Occasional mergers occur. Slowly, the black hole grows larger. Given enough time, some become giants, supermassive black holes, monsters containing millions or even billions of times the mass of the Sun. At the center of our own Milky Way lies such an object, the black hole, known as Sagittarius A. It contains roughly 4 million solar masses, enormous by human standards, yet modest compared to some of the true giants scattered across the cosmos. Some supermassive black holes contain billions of solar masses. Their gravity governs entire galactic centers. Their influence extends across vast distances. The existence of these giants is not particularly surprising. After all, the universe is old, nearly 14 billion years old. That provides plenty of time for growth. The mystery begins when we look into the distant past, because James Webb is not only observing ancient galaxies, it is also observing ancient black holes, and some of them should not exist. At least not according to conventional expectations. The problem is remarkably simple. Growth requires time. Whether we are discussing cities, forests, galaxies, or black holes, size usually reflects history. The larger something becomes, the longer it has generally been growing. Yet Webb has revealed evidence of black holes that appear astonishingly massive when the universe was still very young. Some existed less than 1 billion years after the Big Bang. Others may have emerged even earlier, and their masses are difficult to explain. Imagine planting a seed. The following morning you discover a towering oak tree, not a sapling, not a young tree, a mature giant. Your first reaction would not be admiration. It would be confusion. How did it grow so quickly? Astronomers are asking a similar question, because even under favorable conditions, black hole growth has limits. As matter falls inward, enormous amounts of radiation are produced. That radiation pushes outward, creating a natural brake on growth. A balance emerges. The black hole can grow, but only so quickly, at least, according to standard calculations. Yet some of the earliest supermassive black holes appear to have ignored those limits. They grew too large, too fast, too soon. The same phrase seems to echo throughout the early universe. Again and again, too bright, too mature, too massive, too soon at first. Researchers explored familiar explanations. Perhaps the original black hole seeds were larger than expected. Instead of forming from ordinary stellar collapse, maybe they emerged from the direct collapse of enormous gas clouds. Such events could create much larger starting points, a head start in the race towards supermassive size. This idea remains one of the leading possibilities, yet even it does not solve every problem. Some black holes still appear uncomfortably large, still uncomfortably early, still difficult to explain. Other researchers proposed periods of unusually rapid growth. Perhaps young black holes consumed matter at rates exceeding conventional limits. Perhaps the early universe provided environments unlike anything we observe today. Dense reservoirs of gas, abundant fuel, ideal conditions for accelerated evolution. Again, the idea has merit. Again, it helps. Yet questions remain. And then there are the little red dots, the mysterious objects discovered by Webb that may contain actively growing black holes. If that interpretation proves correct, they could represent a missing chapter in the story. A population of rapidly growing black holes hidden throughout the young universe. Objects that previous telescopes simply could not detect. Perhaps they are revealing the mechanism that allowed cosmic giants to emerge so quickly. Perhaps they are showing us black hole growth in action, or perhaps they are exposing an entirely different process that we do not yet understand. The truth remains uncertain. But one fact is becoming increasingly difficult to ignore. The early universe appears remarkably efficient at creating complexity. Galaxies emerge quickly. Heavy elements appear quickly. Stars transform their environments quickly. Black holes grow quickly. Everywhere astronomers look, the same pattern appears. The universe seems impatient, as though the first billion years contained far more activity than our models anticipated. And that realization has forced scientists to confront a possibility that once seemed unlikely. Perhaps the issue is not any single observation. Perhaps the issue is the framework connecting them all. After all, one anomaly can be dismissed. Two anomalies may be coincidence. But when multiple mysteries begin pointing in the same direction, a larger question emerges. What if the early universe truly behaved differently than we expected? What if our timeline is incomplete? What if important chapters remain missing? James Webb has not disproven modern cosmology. Far from it, the foundations remain extraordinarily successful. Yet the telescope has revealed tensions that refuse to disappear, questions that continue growing stronger with every observation. And as astronomers attempt to piece together these clues, a new picture begins to emerge. Not a picture of failure, but a picture of unfinished understanding. The universe may not be breaking the rules. It may simply be revealing rules we have not fully discovered yet. And if that is true, then the discoveries of early galaxies, chemical enrichment, reionization, little red dots, and ancient black holes may all be pieces of a much larger puzzle. A puzzle that reaches to the very beginning of cosmic history. A puzzle that may force us to rethink how the first chapters of the universe were written. By now, a pattern has begun to emerge. At first, each mystery seemed isolated. A surprising galaxy here, an unusual observation there, a measurement that appeared slightly inconsistent with expectations. Nothing extraordinary on its own. Science encounters such puzzles all the time. Most eventually find their place within existing theories. Yet, the discoveries revealed by James Webb have proven unusually persistent. The galaxies remained distant. The brightness remained extreme. The chemical enrichment remained surprisingly advanced. The little red dots refused easy explanation. The supermassive black holes remained uncomfortably large. Again and again, the same message appeared. The young universe seemed far more mature than expected. This does not mean modern cosmology has failed. Far from it. The standard model of cosmology remains one of the most successful scientific frameworks ever developed. It explains the expansion of the universe, the cosmic microwave background, the large-scale structure of galaxies, the abundance of light elements, countless observations across decades of research. Without it, much of modern astronomy would be impossible, and yet even successful theories can be incomplete. History offers many examples. For centuries, Newton's laws explained the motion of planets with extraordinary precision. Then Einstein revealed a deeper layer of reality. Newton was not wrong. His description simply had limits. Likewise, the discoveries of James Webb do not necessarily imply that our cosmological framework is broken, but they may be revealing places where our understanding remains unfinished, places where important details are still missing. That possibility is what excites many astronomers today, because science advances most rapidly when observations expose unanswered questions. Every mystery becomes an invitation, an opportunity to learn something new about the universe. And the mysteries of cosmic dawn are among the most profound ever encountered. Consider what we have seen. Galaxies appearing surprisingly early. Galaxies producing enormous amounts of light. Evidence of heavy elements forming faster than expected. The rapid transformation of the cosmic fog. Mysterious populations like the little red dots. Black holes reaching extraordinary masses in astonishingly short periods of time. Each puzzle points toward the same era, the first billion years, the universe's earliest chapters. It is as though we have opened an ancient book and discovered that the opening pages do not quite match the summary we thought we knew. The story is familiar, yet somehow different, not rewritten, but richer, more complicated, more surprising. Astronomers are now exploring numerous possibilities. Perhaps the first stars were far more massive than current models predict. Perhaps galaxy formation was more efficient. Perhaps black holes grew through mechanisms not yet fully understood. Perhaps entirely new physical processes influenced the young universe. Some ideas may survive, others may eventually be discarded. That is the nature of science. Questions come first, answers arrive later, sometimes much later. For now, the evidence remains incomplete. James Webb has shown us remarkable new pieces of the puzzle, but no telescope can provide every answer. Each discovery reveals another layer of uncertainty, another frontier waiting to be explored. And perhaps that is what makes this moment so fascinating. We are witnessing science in motion, Not science as a collection of finished facts, but science as a living process. An ongoing conversation between observation and understanding. A conversation that stretches across generations. Every image captured by Webb becomes part of that dialogue. Every spectrum, every galaxy, every distant point of light, each one carries information from a time when the universe was still young, still becoming itself, still writing the opening chapters of cosmic history. What we are seeing today may not be the final picture. Future observations may resolve some of these tensions. New theories may emerge. Unexpected discoveries may reshape the discussion entirely. The universe has surprised us before. There's little reason to believe it has finished doing so. And perhaps the most important lesson of all is this: the deeper we look into the cosmos, the more we discover that knowledge and mystery grow together. Every answer opens new questions. Every horizon reveals another beyond it. Every discovery expands the boundaries of the unknown. James Webb was built to help humanity see the earliest universe. It has succeeded beyond expectation. Yet in doing so, it has also revealed how much remains hidden, how many stories remain untold, how many secrets still drift through space on ancient beams of light. And nowhere is that mystery more profound than in the very first chapters of cosmic history. Chapters we can glimpse, chapters we can study, but chapters we still do not fully understand. To appreciate why that matters, we must step back from the details, beyond the galaxies, beyond the black holes, beyond the measurements and models, and reflect on what these discoveries ultimately tell us about our place in the universe. There is something humbling about standing beneath a night sky. Even in the modern world, even surrounded by technology, even with telescopes capable of peering across billions of years, the stars still inspire the same feeling they inspired in our ancestors. A sense of wonder, a sense of scale, a quiet awareness that we inhabit only a small corner of something unimaginably vast. For thousands of years, humanity looked upward and wondered what lay beyond. The answers were few, the mysteries were endless. Today we know far more than those early skywatchers could have imagined. We know that the stars are suns. We know that galaxies fill the cosmos. We know that the universe has a history stretching back nearly 14 billion years. And yet, despite all that knowledge, the earliest chapters of that history remain surprisingly elusive. James Webb has allowed us to see farther than ever before, farther not only in distance, but in time. Its observations have carried us closer to cosmic dawn than any generation in human history, closer to the birth of galaxies, closer to the first stars, closer to the moment when the darkness began to retreat. And what we found there was not simplicity. It was complexity, not certainty but questions. The deeper we looked, the more the universe seemed to resist easy explanation. Ancient galaxies appeared unexpectedly mature. Chemical enrichment arrived surprisingly early. Black holes grew with astonishing speed. The first billion years became a landscape filled with mysteries, not because the universe was hiding something, but because we are only beginning to learn how to read its oldest pages. Imagine discovering a vast ancient library. Most of its books are intact. The middle chapters can be studied. The later chapters are beautifully preserved. But the opening pages are damaged, incomplete, scattered. The story is still there, yet its beginning remains difficult to reconstruct. That is the challenge facing modern cosmology. We can see fragments of the universe's earliest history. We can glimpse the outlines. We can identify characters in the story, the first stars, the first galaxies, the first black holes. But many details remain hidden between the lines, and perhaps that should not surprise us. After all, we are attempting to understand events that occurred more than 13 billion years ago. Events separated from us by distances so immense that the mind struggles to comprehend them. The light reaching our telescopes tonight began its journey long before Earth formed, long before the oceans appeared, long before life emerged. Those photons have crossed nearly the entire history of the cosmos to reach us, each one carrying a message from an ancient age, a message written in a language of light. And we are still learning how to read it. Perhaps future telescopes will reveal more. Perhaps new discoveries will solve some of today's mysteries. Perhaps they will uncover entirely new ones. That has always been the pattern of exploration. Every horizon reached reveals another horizon beyond it. Every answer becomes the beginning of a new question. The universe does not seem interested in providing final conclusions. Instead, it invites curiosity, patience, wonder, and as we continue exploring the cosmos, one truth becomes increasingly clear. The story of the universe is far larger than any single generation can fully understand. We are not standing at the end of that story. We are standing somewhere in the middle, looking backward, looking forward, trying to piece together fragments of an ancient narrative still unfolding around us. And perhaps that realization is more valuable than certainty itself, because it reminds us that discovery is not merely about finding answers. It is about learning how much more there is to explore. As we drift toward the end of our journey, it is worth returning to the question that has quietly followed us from the beginning. Not a question about a single galaxy, not a question about a black hole, not even a question about James Webb itself, but a deeper question, a question hidden beneath every mystery we have explored. What if the early universe was not exactly as we imagined? For generations, humanity has tried to reconstruct the story of cosmic origins. Piece by piece, observation by observation, theory by theory, and with every new discovery, the picture has become sharper. Yet the closer we approach the beginning, the more the universe seems to blur once again. Not because the evidence disappears, but because reality becomes stranger. The earliest galaxies shine brighter than expected. The first heavy elements appear sooner than expected. Black holes grow faster than expected. Again and again, the universe whispers the same message. There is still more to learn. Perhaps future observations will reveal simple explanations. Perhaps the tensions will fade. Perhaps new data will fit comfortably within existing theories. That is entirely possible. Science has seen such moments before. But perhaps something else is happening. Perhaps we are standing at the edge of a deeper understanding, the edge of a chapter that has not yet been written. After all, every generation believes it understands the universe a little better than the one before, and every generation eventually discovers how much remained hidden. The cosmos is patient. It unfolds across billions of years. It does not rush to reveal its secrets. It offers them slowly, one photon at a time, one observation at a time, one mystery at a time. Tonight, somewhere beyond the reach of our eyes, ancient light is still traveling toward us. Light that began its journey before Earth existed, before the sun was born, before the Milky Way reached its present form. Messages from a forgotten age continue crossing the darkness, silent, persistent, unstoppable. And perhaps, at this very moment, some of those photons are carrying answers to questions we have not yet learned to ask. That thought is both humbling and beautiful, because it reminds us that the universe is not merely a collection of objects scattered through space. It is a story still unfolding, a story that began nearly 14 billion years ago, a story written in stars, galaxies, and the faint glow of ancient light. And despite everything we have discovered, we have only read a fraction of its pages. Somewhere within those unread chapters may lie the explanation for the galaxies that grew too quickly, the black holes that appeared too soon, the mysterious little red dots, and the countless other puzzles waiting beyond the horizon. But tonight, those answers can wait. For now, simply imagine the vastness above, a universe awakening from darkness, the first stars igniting, the first galaxies emerging from the cosmic night, ancient light beginning a journey that would last billions of years, a journey ending here, with us, tiny observers on a small world orbiting an ordinary star, looking upward, wondering, listening, and slowly learning how to read the oldest story ever told, the story of the universe itself. Good night.